Lesson 2, rational and irrational numbers. Okay, I want you to cast your minds back to when you were 5 or 6 years old, when things were much less complicated than they are now. How many of you have ever watched or used to watch regularly Sesame Street? Most of you? Okay. Remember Sesame Street? At the very, very end, when you watch the credits, they would always say, Sesame Street is brought to you by what? The number 6 and the letter E, B. Okay. They always had a number and a letter that show had been brought to you by. Remember that? Really? You guys missed? They end the shows like that. Here's what you never heard, though. Sesame Street is brought to you. You heard this. Sesame Street is brought to you by the number 7. Sesame Street is brought to you by the number 12. You never heard them say, Sesame Street is brought to you by the number 4.3. Okay, you never heard them say a decimal. You never heard them say, Sesame Street is brought to you by the number 17/9 fraction. You never heard them say, Sesame Street is brought to you by the number pi, because pi is a number. And the reason is there are different types of numbers. That's today's lesson. We're going to try and categorize types of numbers. And there's an easy pattern that you can spot on your calculator. And once you spot that pattern on your calculator, you'll notice which numbers have that pattern before you go to your calculator. That's our goal today. So, rational and irrational numbers. Warm-up number 1, it says, convert the number 28/11 to a decimal. How would I convert that to a decimal? Yeah. Good, do it. Go to your calculator. 28 divided by, because over means divided by, 11. Nothing fancy, nothing. Now, I like my calculator. My calculator, instead of a divided by sign, uses a slash, which looks like a fraction, which is nice because I wrote a fraction. I kind of like that. Anyways, what do you get? I get 2.5454545. Does it end there, do you think? Okay. What does it do? Well, thankfully, I have a long number calculator. So we're going to go 28, and we are going to divide by 11. Calculate. That's to 1,500 digits. I think we can reasonably assume the pattern keeps going. Yes? We don't want to write 28.5454545454545. So we said we write it like this. Did I say 28? 2 point. How do I write 545454545? Okay. That's correct. Although I have to be honest, if you're British, you'll do that. I like our system better. So circle the correct alternative in the following statement. This decimal representing 28/11 has a repeating or non-repeating pattern. Let's circle that. And terminates or non-terminates. I haven't told you what the word terminates means, but maybe from the movie Terminator you might have a good understanding. It stops or ends, terminates, right? So this one here is non-terminating. It continues going forever and ever and ever and ever and ever. Compare that with 28/8. What's 28/8 as a decimal? 3.5? 3.5 what? Well, technically 0, 0, 0, 0, but we're not going to count the zeros. We would say this has a repeating or non-repeating? Non-repeating. Don't the zeros repeat? We're not counting the zeros. And terminates or doesn't? Terminates. So far we've seen non-terminating repeating and terminating not repeating. Are there any numbers, are there any examples that don't terminate, so they go on forever, but don't repeat? Yes. There's a famous one right there. But believe it or not, there's lots of them. In fact, there's more of those than the ones that don't. That's actually been proven. And you may think, really? Yeah. For example, try example C, convert root 2 to a decimal. Okay? I'm going to go to my long number calculator. I'm going to delete this. I'm going to put a 2 right here. 2. And I'm going to take the square root. And you know what? Let's go to 5,000 digits. Calculate. And you'll notice I had to do some thinking. My computer, which is way more powerful than your calculator, was doing some serious number crunching. Did you see it spinning for a second there? The answer is 1.4142135623730950. Do you hear any pattern? No. Okay. So, circle the correct alternative.
Wait, is there a symbol for that?
There's not a symbol for it. There's a whole categorization for it. We're going to give these numbers a special name. Repeating or non-repeating? Non-repeating. Terminates or doesn't? Non-terminating. Okay, so here's our terminology. This you need to know. We're going to use these words. Repeating decimals. These are decimals which have a recurring pattern of digits and are non-terminating, don't end. There's a pattern, but the pattern isn't just a pattern. It's the same number of, the same group of numbers repeats over and over. Let me give you an example. This is not a repeating decimal. Hit the wrong button. I do this every time. Still getting used to my new keyboard here. This is not a repeating decimal. 0.010010001000001. Is there a pattern? I think there is. What's coming next?
5 zeros.
Okay, 2, 3, 4 zeros, 5 zeros, and a 1. Is the same group of numbers repeating over and over and over? No, because you're always getting an extra 0. This is not repeating, but if I do this, non-terminating. Then we have non-repeating, decimals which have no recurring or repeating pattern of digits. There may be some kind of a pattern, like the one I just did with you, but they're not terminating, and there's not a pattern or group of numbers repeating over and over. Terminating, that's the easy one. They come to a stop. Decimals with a finite number of digits. Non-terminating, decimals with an infinite number of digits. So, example 1. State whether the decimal equivalent of each number is repeating or non. What would be a good word? You know what? I was going to say R and N, but we also have N for non-term. How about R and NR for not repeating, and T and NT for non-terminating? Fair enough? So A, repeating or not? Terminating or not? 0.125, yes, if my memory is correct for 1/8. A lot of these, because I grew up without a calculator, you memorize some of the simpler fractions. It was easier. 2 over 11. 2 over 11 is going to be, is it 2, 1/8. Okay, so it's 0.18, like that?
Yeah.
Repeating or not? Repeating. Terminating or not? Non-terminating. (9/7). This one you got to be careful. This is where if you have a cheap calculator, your calculator might lie to you. I thought calculators were always right. No, I went on a rant for that calculator thing at the beginning of the year on purpose. When you go 9 divided by 7, I get this. 1.28571428.6. It's not that. It's 285714285714285714. That's a 5, but because the number off the screen is a 7, my calculator lies to me and rounds off to a 6. I'll convince you. What was it, 9? divided by 7. Calculate. And I get 1.2857142857142857142857. Hear it? Because your calculator can sometimes lie, it might be worth remembering certain fractions do repeat. Sevenths do repeat. In fact, most, try that again. A lot of the prime numbers repeat. Not all, but a lot of them do. So, repeating or not? Turns out it's repeating. It looked like it wasn't, it is. Terminating or not? D. By the way, look at D. What is that bar over? The 9 and the 4 or just the 4? So this is 0.944444444. Oh, repeating or not? Repeating. Non-terminating. What about root 8? What do you think, terminating or not? Mr. Duick, I noticed that root 2 that you did earlier, that was also one that didn't repeat and didn't terminate. Are all square roots non-repeating and non-terminating? All square roots that aren't perfect squares, that don't work out evenly. It either works out evenly, comes to a stop. If it goes off your screen, it's non-repeating and non-terminating. 0.16 being a good example. Try this on your calculator. Oh, so that's an example of a square root, and it did work out evenly? So it, repeating or not? Not repeating because it comes to a stop, yes? Oh, and non-terminating. Oh, terminating. Yes, terminating. Sorry. Comes to a stop. Terminating. Okay. We're going to break numbers up into two main categories: rational and irrational. Rational and irrational. Decimal numbers which repeat or terminate can be written as a fraction, and we call these rational numbers. The way I remember it is rational and fractional sort of rhyme. If you can write it as a fraction, it's rational. Pardon me? And irrational can't be written as a fraction. Okay? These are called rational numbers because they can be written as the ratio of two integers. Decimal numbers, which are both non-repeating and non-terminating, like pi, like most square roots, can't be written as a fraction, and they are called irrational numbers. Example 2 says, identify each of the following as rational or irrational. Let's use a capital R for rational. Actually, you know what? I got to take that back because R is going to get used for something else and I is going to get used for something else. Let's use rat, R-A-T, for rational, and IRR for irrational. So let's see. 1.493, is that rational or irrational? It's rational. How would you write that as a fraction, Mr. Duick? How would you write that as a fraction? How many decimals are there? Count. How many numbers are there after the decimal point? If you take the number 1493 and you divide it by that many zeros, 3, there. I just wrote it as a fraction. 1.493, as it turns out, is 1493 over 1,000. Did I say over? That sounded like a fraction. B, root 5. Now, did you try it or did you figure it out ahead of time? Nice. Did you hear Brody? I think it's irrational. If the square root doesn't work out evenly, it's irrational. And I know root 5 doesn't work out evenly. Root 4 is rational. Root 9 is rational. Root 5, root 6, root 7. By the way, do you see why I said it turns out there's more irrational numbers than there are rationals? Root 8, root 10, root 11, root 12, root 13, root 14, root 15, all irrational. Root 16 is not. Root 17, root 18, root 19, root 20, root 21, 22, 23, 24, all irrational. 25 is. You can find lots of them. So, irrational. 2.34734737, ... Now, I think they want us to assume that the pattern continues. I kind of don't like this question because it's possible I could create a number that went 347, 347, 347, 9826 right off the screen. I could. But I think we're supposed to assume the pattern continues, that this is a non-terminating but repeating. If it repeats, does anybody know how you would get 347, 347, 347, 347 to appear as a fraction? Okay. How many numbers are repeating grand total? 3. Go to your calculator. This is how you create repeating fractions. Type in the 3 numbers that are repeating. So Brianna, type in 347. Hit it divided by. How many numbers are repeating? Divide by that many 9s. 347, 347, 347, 347, 347. The 9 times table has some really neat, nerdily cool stuff. 3/4. You know what? I don't need a calculator for that. If you do, I guess that's okay, but you should know 3/4 as a decimal is what? I hope you know it's 0.75. You've seen that one a fair chunk. 0.75, 0.75. Oh, wait a minute. I don't even need to change it to a decimal. Is this a fraction? If you can write it as a fraction, it's rational. So I don't even need to go to a decimal. This is rational, which means E is rational as well. You know how I know? Because it's a fraction. Fractional, rational. F. Does the square root of 64 work out evenly? Now, what this is saying, by the way, in terms of our BEDMAS rules, take the square root of 64 and then make that answer negative. What is the square root of 64? Make it negative. Is -8 a rational number? Yes, it is. It doesn't go on forever without repeating. So, rational. Irrational, square roots and pi and weird things like that. Rational, the other stuff. And for some reason, example 3, this little symbol should be on the next page. But anyways, example 3 on the next page. It says, order the following irrational numbers on the number line. We're going to try and do this without a calculator, because this would be a classic non-calculator provincial exam kind of a question. First of all, look at all 5 of those numbers. Are any of them negative? No? So you know what? Let's put 0 right there. We're going to try and do some math in our head. Skip A, we'll come back to it in a second. B, what's pi as a number? 3, you know what? I'm just going to write down underneath here 3.14. I'll put it a bit to the right of 3. How far over? I don't care. I'm just doing a rough sketch. Let's go back to A. Does the square root of 14 work out evenly? No. What's a square root close to 14 that does? So what's the square root of 16? Is 14 a little less than 16? I think the square root of 14 will be a little less than the square root of 16. What did you say the square root of 16 was? So if I have to guess for the square root of 14, 3.9-ish? Ish? Okay. I'm going to write, I'll put a little question mark there. Ish, give or take. I know it's bigger than pi. I'm pretty sure. So I'm going to put it to the right of pi. Square root of 80, does that work out evenly? No. Is there a nice square root close to that? Oh, 81. What's, Alex, the square root of 81? 9. So what do you think the square root of 80 is? A little less than 9. Take a guess. Sure, I'll call it 8.9. Ish. D. D says 2 times the square root of 15. Does the square root of 15 work out evenly? No. Is there a nice number close to 15 that does work out evenly for a square root? Oh, what's the square root of 16? What would 2 times 4 be? 8. So the square root of 15, a little less than the square root of 16. 2 times the square root of 15, a little less than 8. 7.9-ish? I'll put a question mark because we're doing kind of a rough estimate. Square root of 0.1. I don't know. Oh, that answer, bigger than 1 or smaller than 1, do you think? You're going to get a decimal. Yes? I'm going to write here. Decimal. So of these 5 numbers, one of these things is not like the other one. One of these things just doesn't belong. A little Sesame Street game for you. Let's put them in order. Which of those 5 guesses is the smallest one? E. So let's put that, how about right here? Here's the square root of 0.1. I know it's the closest to 0. What's the next biggest guess that we have? I think pi would be over here somewhere. What's the next biggest guess that we have? Root 14. And you notice we did this in theory without our calculator here. What's the next biggest guess that we have? 2 root 15? Doink. 2 root 15. What's the next biggest guess that we have? Root 80. We get all 5 on there? They're in that order. I'm not sure how far apart they are away from each other, but since they didn't give me any kind of a scale on the number line, Anthony, I don't care. I know that's the right order. I know that the smallest of those 5 is root 0.1, and the biggest is root 80, and the other ones are in between somewhere. The number system. So let's categorize every number that's ever existed. The real number system, recall from the beginning of the lesson the definitions of rational and irrational numbers. We have numbers that either repeat or terminate. Rational, those can be written as fractions. How? Oh, if it's repeating, put it over that many 9s. If it terminates, put it over that many 0s. Then we have irrational numbers, numbers that can't be written as a fraction. Pi, most square roots, and they're recognizable in their decimal form because they go on forever without repeating. If we combine them, if we take all of the rational numbers and we put them in the same bucket as all of the irrational numbers and we shake them up, we have a combination. We call these the, try that again, Mr. Dewick, R-E-A-L. This is the set of real numbers. And these numbers can be represented on a number line. Why do they call them real numbers, Mr. Dewick? Because, and I kid you not, there are also some numbers that are imaginary. They're called imaginary numbers. I'll talk about them someday when we're bored. But there are actually imaginary numbers that show up in math, and we use them, and they actually solve real-life problems in physics. So let's start to categorize numbers. The very first thing you do when you're a small child, or if you have any nieces or nephews or younger brothers or sisters, you may have noticed them going through this. They learn to count, the counting numbers. They learn that they can ask for 2 cookies or 3 cookies. But you will almost never hear a child say, I want 2.5 cookies. And you'll never hear a child say, I want 0 cookies. We call these the natural numbers. The natural numbers are 1, 2, 3, 4. What's next? What's next? What's next? What don't you hear? No 0, no decimals, no negatives. We call them the natural numbers because if you look out in the field, you can say, look, there's 3 cows. There's 5 cows. You can't say there's 6.8 cows, not unless something's gone horribly wrong, right? Oh, and you can't say, it doesn't make sense to say, look, there's 0 cows. Where? There's 0 cows. Doesn't make sense. And it certainly doesn't make sense to say, look, there's -3 cows. So that's why we gave them the name natural. They appear in nature. They're the ones you learn to count on your fingers. Okay? Then we take the natural numbers, 1, 2, and 3. We add 1 number to get the whole number system. Can you see, looking at this list here, which number we added? 0. And there's a dumb way to remember it. This is how I always remember it. The number 0 does look like a hole in the ground. That's the whole numbers. Okay, 0 is the whole numbers. Add a 0. Whatever works for you, but it works for me. Okay? So natural numbers, the ones that appear in nature, 0 really doesn't. Whole numbers, okay, still no decimals, but let's start counting at 0 because we want to be able to say there's nothing. Then there's the integers. What are the integers? Negatives. But no decimals still. This, while it's negative, is not an integer. By the way, what symbol do we use for natural numbers? Capital letter what? What symbol do we use for whole numbers? Capital letter what? What symbol do we use for integers? Capital letter what? That's why for irrational I didn't want to use an I. I knew this was coming down the pipe. Okay? Then we have rational numbers. What's the symbol for rational? Unfortunately, R is taken for reals. We can't use R for rationals because real numbers are so important. We use the letter R. So instead we use the letter Q. Why Q? I'll tell you why. What is this little horizontal line right there? When I write it as a fraction, what mathematical operation is that? Adding, subtracting, multiplying, or dividing? Dividing. Does anyone remember when you multiply, you call the answer a product? When you add, you call the answer a sum. Does anyone remember what you call the answer when you divide? Quotient. That's why we use Q. Q for quotient. We say, you know what? If you can write it as a fraction, it's rational. So we symbolize that, Curtis, by saying a number divided by another number. Oh, but we get fussy. Where A and B, that symbol right there, this curly little E right here, means belong to. Where A and B belong to the integers. So, Amy, we're going to say, don't be doing rational numbers like this. Don't put decimals over decimals in a fraction. That's just sloppy, yucky math. Oh, and we also say B can't be 0 because you can't divide by 0. Why can't you divide by 0? No, you don't actually get 0. Why can't you divide by 0? Put your pencils down, look up. Angela, sit up. Very simple reason. Watch. We'll do some math in our head. If I tell you 6 divided by 3, what is 6 divided by 3? Brianna, that also means that you can go backwards. 2 times 3 is 6. Supposing you could divide by 0, supposing you went 6 divided by 0 and you got an answer. Let's call that answer x, because I don't know what it is. Marcus, that would have to mean that you could go backwards. That would have to mean that x times 0 was 6. What's wrong with that line? Darian? We can have our 0 times table, or we can have 0 dividing. We can't have both. They contradict each other. So it's really because it doesn't work backwards. It's not that the answer is 0. It's not. The answer is undefined. There is no answer. If there was, we'd lose our 0 times table, which is actually really, really important. Pick your pencils up. Nerd note over. Okay? Then we have irrational. The symbol for irrational is Q bar. Rational, that symbol there means not rational. Irrational. If you put the rational numbers together with the irrational numbers, you get the reals. So we've come a ways from Sesame Street is brought to you by the number blah, 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 and the letter blah, blah, blah. We're saying, you know what? Types of numbers there are. Naturals, 1, 2, 3. Whole numbers, 0, 1, 2, 3. Integers, -3, -2, -1, 0, 1, 2, 3. Rationals, anything you can write as a fraction. An integer divided by an integer, as long as you're not dividing by 0. Irrationals, weird square roots, pi, the weird stuff. Put them together, and you got the reals. In fact, we can draw this as a picture. So what I'd like you to draw in the middle of this picture is a little I can use my fancy schmancy draw tools. I'm going to go thunk. Draw a little rectangle about that big. Or it can be a circle. But this is going to be, and I can even type. Cool, 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 cool. Natural numbers. What are the natural numbers? 1, 2, 3, 1,000, 319, 1,000,000, 1,000,000,000, trillion. They're all there. Then draw a slightly larger circle or rectangle that swallows up this one, kind of like that. This is the whole numbers. The whole numbers include all of the natural. In other words, if you know a number is natural, you know it's also whole. What are the whole numbers? All of the naturals, and we added one more thing, the one that looked like a whole. That's a terrible looking 0. Add 0. Then we zoomed out one more time. We swallowed up all the whole numbers, and we made the integers. What are the integers? All of the wholes, all of the naturals. Negatives with no decimals. I got to be careful because kids always want to say, isn't negative 0.5 an integer? Because negative, no. No decimals yet. So, -3, -2, -1, and I'll put a ... in front of the -3 to show that it goes that way forever. -224, -1,000,000, -1 billion, -1 trillion, -1 quadrillion, -1 quintillion. He keeps going. Okay? And then what we do is can I do this, Mr. Dewick? I'm going to have to go a little bit smaller. Will it fit? It will. No, I don't want to go up. There we go. Close enough. These are the rational numbers, and these include any fractions. Give me a fraction. You know what? Let's go negative 2 over 5, just to remind us that it can be a negative fraction as well. It includes decimals, like 0.63. It includes repeating decimals, like 0.1223, where the 223 repeats. 1, 2, 2, 3, 2, 2, 3, 2, 2, 3, 2, 2, 3, 2, 2, 3, 2, 2, 3. Why did I draw a vertical line separating? Well, now there's no overlap in this set over here. Over here, these are irrationals. What are these ones? Pi. Most square roots. Root 40, I know that doesn't work out evenly. Root 5, root 6, root 7, root 8, root 200, root 199, root 188, anything that doesn't take the square root of evenly. Oh, let's do the weird decimals. 0.136492 ... So I didn't have any kind of a pattern there. And then we also said the weird one where there's a pattern but not a specific set of numbers that repeats, like this, for example. 0.1112131415. What comes next? 16. Then? Is there a pattern? Yes. Is the same group of numbers repeating over and over? Nope. Then, put these together, and you have the real numbers. So there is, I think I can make this a little smaller so you can see the whole thing on one screen now. There is a good picture using what's called a Venn diagram, a nested diagram, showing you how, any number that's natural, is it automatically inside the whole number? Then it's automatically whole. Is it also automatically inside the integers? And any natural number is an integer. Is it also inside the rational? Yes, that's also a rational. Oh, and is it also inside the real? Yes, it is. But you can see the integers aren't necessarily whole or natural. Some are, some aren't. So, example 4 says, for each of the following, write all of the sets of number to which the given numbers belong. I find it easier to start from the outside in. So the number 9, is it real? Yep. And the symbol for real was a capital R. Is it rational? Can you write 9 as a fraction? Yeah, 9 over what? 1. What was the symbol for rational, remember? Q. What comes next in our picture? Is it an integer? Yep. It's a positive integer, but it's an integer. Is it a whole number? Yep. Is it a natural number? Yep. That's why 9 is a number you guys are more comfortable with. You'll find The further out we zoom from the middle, the trickier the numbers get, the less comfortable, the trickier the math gets. 11 over 7. Is it a real number? Yeah, everything right now is a real number. Is it a rational number? Can you write it as a fraction? Mr. Dewick, it is a fraction. Oh, okay, good point. Q. Is it an integer? No. Oh, then we're done. Because if it's not an integer, then it can't be a whole and it can't be a natural. Let's make that Q a little bigger, better. Root 5. I heard someone whisper it. They're right. Irrational, right? Is it a square root that doesn't work out evenly? Then it's irrational. What was the symbol for irrational? Not IRR. Q bar, not rational. Four, -7, start on the outside. Real? Yes. Oh, we should have said that this was also a real one, the root 5. Everything in your grade is going to be real. When do we do the non-real ones? Later. Not this year. Although I'll show them to you later on. -7. Real? Yes. Rational? Can I write it as a fraction? Yep. What comes next? Is it an integer? Is it a whole? Oh, it's not, because the whole numbers have to be positive. Okay, stop there. 5, 3.14 ... I think that's supposed to be representing a specific number. Which number do you think that's supposed to be representing? I think that's supposed to be pi. Pi, I know it's real, but it's irrational. What about the last one? Root 8. Well, it's real. Thank you, Captain Obvious. Irrational, which means Q bar. B says, explain why 9, the first example, belongs to 5 number sets, but -9 only belongs to 3 sets. We're not going to write it down, but negatives can't be a whole, can't be a natural. So you've removed 2 sets that you would normally belong to. Okay. Which one? A? VI? Try square root of 8 on your calculator. It doesn't work out evenly. Square root of 9 does. It's irrational, trust me. Okay? Can you get your textbooks out, please? Sounds like someone didn't bring their textbook. Oh, they did? Okay. And open to page 211. And what I wrote down for homework. Now, a few of these that have weird roots you won't quite be able to do, but I want to get you started on this so you can try from page 211. Number 3, 4. Now, some of them are talking about cube roots and fourth roots. We did play with our calculators a little bit, but I'll be doing that actually in Wednesday's lesson. So if you're not sure how to handle those ones, don't freak out just yet, but I want to get you started. Seven is good. 10's going to come later. 11's going to come later. 14 is good. And we will pause there. There's about 6 or 7 minutes left. Let you try that. Okay.